So that was kind of, I got interested sort of out of that whole piece about, well, gee, if I can just get this bit stream, there's useful things to do. And then there was the problem about, well, how do you get the bit stream? What is this whole bit stream communications? How do you go from there? So what gnuradio is really about is creating a platform where we can actually, people can learn about digital communications. If you go to university, you can study, but there's a question about what tools are available. Maybe there's some very expensive tools, there's some not so expensive tools, for example, MATLAB or something like that, where you can set up some models of communication systems. But it has the property that you can't really run the system. They're not built for real time. So I'm sort of bent as an engineer. I like to actually build it and see them work. So we did that. The other thing that we're looking at is actually building once you start looking at signal processing, it turns out that it doesn't matter too much what the signals are. There may be some question of how I get the initial signal into the system, but whether it's radio, or whether it's sonar beam pointing, or whether it's like ultrasound imaging, like fetal conditions, it's all pretty much the same. I had a question a while ago, well, could this be used for temperature monitoring? The answer is yes. It's only a question of what's the front end that you've got that you put into the system. And so about gnuradio, it's free software, so it's under the GPL, available for anyone to do anything they want with. We don't have any particular goals to build a commercial product out of this. Our emphasis is on actually deploying something on commodity PC hardware initially, because what's happened now, if you look at what's available, is that although traditionally radios may have had DSPs in them, it turns out that if you're willing to throw a temporary workstation class PC at it, it's got 20 minutes. The DSPs may be cheaper, but you can do the same amount of work with your 1.7 gigabit thing. And that hardware gets cheaper and cheaper without us having to do anything. Just wait next year. Let me talk a little bit about software-defined radios. That's sort of what happens here. The way I like to think about software-defined radio is it's about really getting the software as close to the antenna as I can. So it's about turning as much of the problem into a software problem. This has to be as opposed to a hardware problem. I've been in a position where I've done a fair amount of hardware design and a bunch of software design, and personally I like software design better. It's faster, it's quicker turn. It's not these aren't great things that you can do with hardware, but if you look at, well, how fast can I maneuver, software is the fastest thing. The other thing about with software-defined radio is it actually, the software continues to define the actual waveform. So there's this whole spectrum you can look at about, well, there's processors and there's radios, and where do I draw this boundary? And we'll cover that in some detail later on. But you can start with something where you had like a conventional analog radio that may have, like for home use, something an FM receiver, which really fundamentally an analog receiver. It may have a digital display on it. It may have a digital PLL that sets the frequencies, and fundamentally it's an analog device that has some digital control on it. Up from there, you may look at things like cell phones, where there's an RF piece to the thing, and then there's a DSP doing some of the communication. But if you look at your classic cell phone, for example, this cell phone, although it operates over here, it doesn't work in the U.S., even though the frequency bands aren't that much different. Technology. So one thing that becomes possible, and one of the commercial things driving software-defined radios, specifically multi-mode base stations, because the idea is that if I really turn this into a software problem, then I can roll out new features, new upgrades, and all this cheaper. So the UMTS stuff is specifically looking at this. If you look at sort of there's good and bad parts about it being hard to roll out. If you look at the location-based information services that are coming specifically in the U.S. that everybody's going to end up with them. In the U.S. it's under the enhanced 911 service. There's a public interest in knowing where you are in case you're injured. And I'm like, if I get hit by a car, I'll call and worry about it. As opposed to like just turning the locator on all the time. So you get this whole opportunity of how much of this is really software. So you can get to cell phones today. There's a fair amount of it software, but the fact that this cell phone doesn't work every place else, it needs to be really different. In the U.S. the same situation where we have a little bit of analog stuff still left. You've got the IS-136, which is a TDMA. It's basically narrow channel spacing. You've got GSM, and you have the Qualcomm CDMA, all concurrently deployed. Where I'm headed with this whole thing is the idea is that we should be able to transmit and receive a signal. Now, there's some questions about hardware over here. Gee, how do I get a signal out of the antenna that I can deal with? But if you just keep looking at the processors, get faster, 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 we try to push these things closer and closer together. We'll talk about some of the little hardware tricks that you end up wanting to use because maybe I'd really like to do a little bit more and I'm willing to throw some hardware in. Particularly if you start looking at throwing FPGAs at, where you're basically still maintaining the ability to program the whole system on the fly. The other thing is to really expand. I got interested in this radio, like I said, about looking at this. I grew up not experimenting with built a crystal radio set and was amazed that, despite driven into the ground, there's a piece of wire I can actually hear the local AM radio station. But I'd like to really see what are the tools available on the computer. There's all kinds of interesting signals out there, and you should be able to pull them down. The other thing is to really expand the free software point of view or ethos into what have been traditionally hardware-intensive areas. It's not that there isn't like free software people working on either like the open cores or the free CPU kind of thing, but really to hear if we can, again, turn it more into a software problem, there's opportunity for more people to participate, there's more to stop faster, and provide a platform to build on. Okay, I'm going to talk a little bit about radio, just to start with. Who here actually knows how radios work? Okay, good. When I first, I was trained as an engineer, and then went into operating systems initially, a whole bunch of networking stuff. And, did all the physics and everything, but I was always kind of like, okay, radio, let's see. That's, first of all, like, hey, it's an analog, which isn't that sort of black magic universe where you can't just pretend it's all ones and zeros. And this is actually, that's a 1910 vintage spark gap transmitter and receiver. We've got the transmitter here on the left, and then the receivers, the two light bulbs that you knock the tops off the light bulb and fill them with water are two crucial pieces of the receiver. We would call these wideband jammers right now. Literally prohibited. There's like zero tuning on the transmitter, right? You basically just got the frequency transmitted, really whatever the frequency of that spark is. You've got, if you look at the spectral distribution of it, it gets really broad. But anyway, you can just hook this baby up and turn it on, and bothering all of your neighbors. But one of the things that looked at me, I said, okay, radios, how do they work? What goes on? And there was this mysterious, to me anyway at the time, this up conversion and down conversion. Yeah, people have told me, yeah, you just like shift the frequency up and shift the frequency down. Finally, I cornered something and said, okay, really? There's one tree identity that you have to know that pretty much explains everything. This is the first order hand wavy level. And it's the product of two sine waves or cosine waves. Out of that, you get the sum of the two, you get the frequency component that's the sum of the two, and one is the difference of the two. So you got multiply two sine waves together, cosine waves, you're going to get one frequency component out that's actually the sum of the two, and the other, which is the difference of the two. You kind of go, okay, so what? Well, basically, you can shift everything up or down by this amount. Now, you end up with two signals on the output, you're going to generally want to throw one of them away. This is the basic math that's behind the whole thing. And where we illustrate this multiplier here, because it's really, from a software person's point of view, it really is a multiplication. In the hardware, they do it a couple of different ways. Typically, they've got this thing called a double balance mixer, which is a non-linear device that pretty much has this math happening. There's solid-state versions with filtered cells. And they have a few non-ideal properties that when you really start to build radios, you've got to worry about. But fundamentally, this is the piece that's happening. So the illustration here is just, let's say I've got an 800 megahertz signal. It's coming in. It's got 800 megahertz plus my signal of interest on it. You can just imagine it's AM modulated. So it's just how loud, what is the amplitude of the signal as I talk. And if I multiply it by the 790 megahertz thing, I'm going to get a 10 megahertz signal out and a 1.6 gigahertz signal out. If I somehow manage to throw away that 1.6 gigahertz signal, then I've effectively down-converted or translated this 800 megahertz signal, it has my signal of interest riding on it, down to 10 megahertz. So, yeah?
Will the 10 megahertz thing also have to be same exact computation system?
Yeah, they'll have, they're both in both places. then it's a question you get to throw one away. And there's a bunch of tricks, like for example, we can talk later, like I'm going to present sort of regular superhead radio and then kind of software version and how they go. But there's a bunch of different trade-offs you can make, and there are engineering kind of trade-offs, because this can be a complex multiplier in software. Hard to do complex multiplier in analog hardware. That's the tricks you can do where once you've got, hey, it's all this, right, and you can go to 10. So you get both of them out, and then there's all kinds of tricks that occur. So this is this would be a double conversion, super heterodyne radio. And I think the super part of it was, a marketing thing, and the heterodyne was external force. So the whole idea is I got an antenna out here. This is hard to steer up, but you got an antenna here. These things are gate blocks of some kind. So this would be called the first low noise amplifier. This would be a bandpass filter, which effectively just chops out, just only passes certain frequencies and leaves the others out. This is one of the big things that we can talk about, effectively like a multiplier, a couple more of these. And this is really the strategy that pretty much every radio built in the last 50 years for sure is done this way. Your cell phones and everything. There's a difference in how many of these mixers occur in certain radios, but the basic layout tends to be the same. How you tune one of these things is actually this variable oscillator. Is you twist this knob, and you can think about this as a signal of interest is over here coming down the antenna, and it's at a particular frequency, so in one sense we think about it's a fixed part. And by twisting the variable oscillator, I can basically, I'm going to get an answer out here that's going to be usually either the sum or the difference that I'm interested in. So this piece in here is called the IF, or intermediate frequency, which in these radios, you pick one that you like. And there's a bunch of engineering trade-offs to make. An FM receiver is typically 10.7 megahertz. In various communication receivers with different values, microwave stuff, radar stuff, or either 70 megahertz or 140 megahertz. It varies, but you pick a fixed piece in here. So you end up with like this answer in here, the frequency in this area here would always be presented FM receiver 10.7 megahertz. So by varying this here, I get to basically select whichever difference it is, and I can steer that through. Why they do this is because these filters are hard to make such that they can adjust on the fly. So the idea is I can build this bandpass filter with a fixed set of specifications. It's centered at a particular frequency and has a particular transfer characteristic that's relatively easy to do. Making them variable is doable but expensive, and people don't like that. And then what end up is you've got usually another fixed oscillator that's just going to knock the signal down. This is a fixed signal, this is a fixed place, plus with your signal writing on it, and then this knocks it usually down to some other place. And then on the back end of this thing, there's some kind of what we call a detector, but it's really where I'm going to look at what comes out of here and say, is this analog? And maybe here's my radio signal, my broadcast radio signal, audio-wise, and my FM signal. In the more interesting contemporary world of digital communications, the detector really turns out to be some kind of fancy modulator. We'll come back to this a couple of times. But you okay so far? Just got questions here as far as the group? Okay, so in this detector zone, we've got a bunch of different kinds of modulation that could be applied. Now, a lot of these are traditional ones that go back way to the beginning of time. So we've got this amplitude modulation. This actually here are back to the, remember the picture of the spark gap kind CW or more is kind of either the presence or the absence of the signal. AM is the next one down. FM. These AM and FM there are very simple analog solutions for them, and partly why they were deployed. They're easy to transmit or easy to receive. Getting up to what's currently used in modern digital communications, we've got phase modulation, PSK, phase shift, quadrature amplitude modulation. Then it gets, once you get to QAM, which is I've got what you call an in-phase to quadrature signal, which I can do a bunch of things with, we're not going to get here. Then there's a whole bunch of variations on it. And then it starts to be whether it's a continuous signal that's being modulated, or, for example, in our cell phones today, they're actually burst modes, and that they're usually time division, multiple access. So what happens is you have a little tiny window where they transmit to your phone, and your phone transmits back, and you may be sharing it with 8 other people at the same frequency. So there's some tricks in that about, boy, I've got to like sync up with the signal, and I've only got like a millisecond to establish synchronization before the signal's done flying. So Then what does all this got to do with DSP and why did they do it? We look at this, where DSPs first got applied in this situation, we were on the far end, on the detector. So they started looking at, can I build a better receiver using DSPs? You'll see that in contemporary communications receivers. The cell phone stuff all had to be that way. And the arguments for why would I do this is that they're cheaper to build. There's no manual adjustments in it because you think about DSP stuff, the software doesn't change. So you don't have like an issue of tolerance and things like that. Well, the hardware, there's no variations from unit to unit. So it's a manufacturability issue. If you look at, if you ever opened up like the classic transistor radio, the little thing, if you look in there are usually about these little metal cans, the little screwdriver slots on top of them, and they hated them. If you think how those got built, they're usually like in China, somebody with a plastic screwdriver and they twist it. And that's how it's gotten done. That's why the guts of most TVs are built in China. The labor costs are going to put those out. So this is one that's getting out. Okay, so now let's take a look at what's possible today. I'm going to do just a little survey on kind of what hardware is available today, where is it headed, and then we'll get back to specifically the radio. So if the game is to get the software as close to the antenna as we can, it turns out that today the limiting factor is the analog to digital converter and the digital to analog converter. So on the receive side, basically today you get a 14-bit converter running at 65 million samples per second. Now that is actually pretty good. It's and these are happened to be analog devices parts. They are the best ones available today. Not partial, but the best parts. And they're relatively these are parts that are targeted at cellular base stations. And small quantities are about $40. You're okay. But what you can do, start thinking about what you can do with 65 million samples per second. You can, there's a Nyquist theorem that says minimally you need twice as many samples per second as you have bandwidth of interest. And if you want a little engineering margin, and you cut this down to like 50 megasamples per second, everything that could really deal with 25 megahertz worth of bandwidth all at one time. So now what's pretty interesting then is if you look at, for example, in the US market, you look at the cellular, we have an A operator and B operator that are adjacent to the frequency allocation, and the two of them together takes up 25 megahertz. So you could conceivably build a unit that has a no-tune front end, like a fixed tuning front end, and with one RF front end and one A to B converter, you can pull down all of that data all at the same time. So this is the key piece to this whole game is all of the data all at the same time. There's no like knobs to twist on the RF side of the thing. And then transmission, they can transmit faster. It's simply a problem. So this is where we can go today. There turns out to be, if you start thinking about, okay, I want to take one of these converters and I want to stick it on my Pentium with my PCI bus, what happens, and basically we've got this big data stream into really a relatively small bus. So there's some problems today. If I wanted to drop 65 megasample, they take 60 bytes per, 130 megabytes per second, it won't fit across the PCI bus. But this problem is going to go away one way or another. It's either going to go away with 64-bit PCI, 66 megahertz PCI, or just faster way to get the, it could go with FireWire, or bypass the PCI bus. So from our point of view over here on the software side of the universe, we think this is basically a problem that's going to solve itself. But it's one of those places where you start looking, we've got these smoking fast processors today, but we sort of thought about how do I get the data into to make it drain out. And one solution that people have commercially used to solve a piece of this are these things called digital down converters. It's reasonably visible. This happens to be a great chip part, but it has 4 of these things. There's user inputs. What happens out here is there's analog to digital converters out here, so then you have digital data streams coming in here. So this thing has a much front end. And then it's got 1, 2, 3, 4, and then an output. But one channel right here, basically if you look at it, it looks pretty much like a block in that superhead radio picture. So we've got this thing called the complex NCO, which is numerically controlled oscillator. Which you could think of it's like although it's not implemented this way, it's like a sine table lookup thing. You just have a phase value and you go say, what's the sine of this phase? And they happen to be looking at both a sine and a cosine at the same time, and then they do a complex multiple after. So they get what's called an I signal and a Q signal at the same time. And then all of this stuff is basically, they're doing filtering. So we saw the block that says filter. And in here, they're generally in these, part of the game you want to do is you've got the signal coming in at, say, 65 million samples per second. This is the data rate up here. And ultimately, what I want for doing my signal processing at the baseband is typically something that's running about 4 times the symbol rate. So if you look at GSM, the bandwidth is about 200 kilohertz band spacing. You're going to want something like twice that. You're going to want 400 samples per second out. So you're fitting 65 million samples per second in, and you're going to really want something in the neighborhood of 400 samples per second out. So the trick is, by steering this NCO, I can effectively tune, because this is just a numerically controlled oscillator, and I multiply the signal coming in by this, and then I want to just, by basically twisting this knob, I select which one I want, and then I filter out all the aboves and belows, and I get what I want. And then they decimate from here, and then that this resampler is for interpolation. It allows me to basically get a lot of pictures and all. So the bottom line of these devices is they let you come in with that very high data rate, knock it down on this ASIC, which could be an FPGA, and it can be a software. If you've got the bandwidth to get it in, this thing's not doing anything you can't do with the CJ. That's the thing to remember. In the perfect, like the extreme in these software radios is the virtual radio, which is really somehow I've got the antenna plugged directly into the code, right? And in that case, all of this is done. It's all software. Somehow I've got an AV converter or somehow. In the ideal universe, maybe we'll get there sometime. I've got a gig sample AV. You've got 2 gig samples. Okay, then how these get used is, so basically the advantage of this whole game is one RF front end. You've got this RF down converter that takes my 800 900 megahertz signal, it's in the cell phone example, and it's going to knock it down, convert it to something that the AV converter can stand. So maybe it's down to the 65 megahertz zone, all depends. So I got one AV converter, and then in this picture they show how taking that output and concurrently applying it to 4 of these quad chips that we just looked at. So what happens is you can think, well, these quad chips could all be software as long as you got big. But the point is I got one RF front end in here, and I got 16 separate channels selected, all coming up at the same time. Now this is actually very interesting because it means, for example, you can watch TV on all your channels at the same time without really. I mean, some cable, I don't know, the cable situation is the same here, but some cable receivers will do a couple channels at a time in the US and get a picture. But conceivably, you could receive all of the broadcast FM stations at once. You could, for example, in a cellular situation, watch all of the paging channels of all of the cells that you receive based on the power sufficient. You could watch the paging channels plus the traffic all at the same time. All right, now let's go back to gnuradio as it's currently in its current state. This is the question of, well, what hardware is required? Let's say I want to play this game. What's what? Well, things running on Linux. It's our sort of favorite development platform, real simple, the basic access to everything. And there's 2 ways to play. The place that we've been looking mostly is really trying to drive the AV converter as close as we can to the antenna, and we're willing to pay some money to get it there right now. So we're using a 20 million sample. We've got a commercial off-the-shelf AV converter board that will get 12-bit samples at 20 million samples per second. Now that's not the ideal, but it's something to provide today. That'll allow us to deal with an input signal that's at least 6 or 8 megahertz wide. That has a tune. So as far as working out all the software and all the math, you got to solve those things that are problems, and then they present you with a wider, but really not some consequence of what example. Now there's other people who have done some of this ESP-based stuff that are really looking at either for like real weak signal work, and they're still working narrow bandwidth. So in those cases, and you may have heard about these people who got like pager demodulators, something with their scanners. that whole same strategy would work. And in that case, you basically end up using a sound blaster, something that is an accepted codec, and you're feeding just a much smaller bandwidth signal. But either of these two solutions gets you into the game. There's different things possible with the two. I mean, one gives you more flexibility to use the software resources. Okay, then the question is, someplace in here, we still haven't managed this magic of getting the antenna into the software, so we've got some kind of RF front end. How we got started, the first thing I started with was just a discrete AM FM radio kit. It was a 14 transistor thing, which had the advantage of you could poke around with and see everything. And then what we've got ordered right now that we think is going to be really deluxe is the cable-ready TV tuner. They're actually the modules that go inside the television. And they're relatively inexpensive, they're about $30 US. And they'll tune over a continuous range of 50 to 850 megahertz with a 6 megahertz bandwidth. Now that happens to dovetail perfectly with the card that we've got. You should assume it starts actually probably Okay, now a little bit how what we're actually using. This gets us signals in the AV converter like something like that. So I looked around for some code base that we could start with. We certainly want to start from zero. So we're going to see what's this mean. And what the most attractive piece of code that I could find was it's called P-Spectra, and it came out of the MIT Spectrumware project. And that project been running for quite a while. Looks like they run quite a few graduate students through it. And their goal was the same as ours, which was to really get the software as close to the internet as possible. They built a big C++ framework that does all of this. Basically demonstrated a bunch of first principles. Had some pretty interesting hooks in it for it. It was really a second generation product. They started service with the very first thing where they just had coded up signal processing blocks and C, pipeline them together. But they had the problem that you really want the control typically to run from the sink back to the source and then the data flows one way. So control goes one way, data goes the other way. So what they came up with this framework, which is what we're currently using. And it's a very clever thing in that what they do is abstract it out of all the scheduling requirements. You basically write a single module with a C++ class and it drives to the base class. It provides two main entry points, one of which is called forecast and the other is called works. Now what happens with forecast is you as a module get asked to please produce n bytes starting at this offset in your output. So they talk about all of the output streams that are indexed by 64 bit numbers. So anyhow, you say, well, for me to do that, I need these input ranges on each of my inputs. So first thing you do is you start the schedule starting from the sinks where the data is ultimately flowing into your display, into the speaker or something like that. And you schedule backwards. You say, well, if you want this, then I got to do this and go forward. And then it schedules this and it takes a look at things like cache sizes. It really tries to maximize the performance of the whole system. And then it basically, when you schedule everything, then it works from the sources of the data all the way. Okay. What you get for this is all the linear speed up with SSD, which is really good. And it uses the signal processing modules themselves are quite easy to write because they have n inputs and n outputs. They've also got a bunch of clever hacks in there that they implement what is traditionally only available on DSPs with hardware support for circular buffering. And if you've ever done much DSP work, there's always usually some history buffer in a finite impulse response filter, a FIR filter. And typically there's regular DSPs have really strange architectures that include the ability to increment pointers modulo or something and do it all. But these folks came up with is a way of they just memory and use nmap to map the buffer twice so that actually does the we talked about forecast and this. What's available right now on the web if you want to come play is the homepage, www.gnu.org, software/gnuradio. And there's a mailing list that discusses the GNU radio requests. Actually, if you just remember this first one, somebody else is playing it. And then there's archives of the mailing list available. Well, we've got, so this is the big picture, where we are right now is we're in the walk phase of the game. So what we've got is this big code base we're trying to get sorted out and build some complete examples of work, sort of the hello world of this gnuradio. And one piece of this whole thing is to get a complete signal change that works from the receiver all the way through. As a simple example, just keep it straightforward and simple. And then the current short-term goal. What we see is some opportunities here for people who are interested is we're going to need introductory and advanced demos. There's a video that we're currently using from PT, there's some more waterfall diagrams, there's all the FFT codes and both spectrum analyzers and all that out of it already. There's people in the audience that are interested in radio signal processing in general, there's some big opportunities we'd like to be able to work on the first node receivers. So that's requires the first node modem, equalizers, and then from there on up, it turns into pretty much looking like the networking protocol. Start looking at the protocol stack and stuff as well. So that's pretty much what we've got in the short-term future. Any questions at this point? Yeah, absolutely. The question is, what is this activity used to test wireless protocol? And the answer is yes. So when I first heard about the problems with RCDs on the wireless and stuff, I thought, oh, here's a perfect example. And it would give us an opportunity to build, again, a small amount of RF hardware that we could probably buy off the shelf because it's really 2.4 gigahertz receiver. Either A or B converter, and then at that point, a simple matter of programming to build an 802.11 receiver. Now, it turns out that I think that we found that most of the cards that in this case receive order is sufficient number of them to converting desirable centrics on the shelf. But the point is, we could get access to it and really do the security testing for this thing. So it's no longer that I got to trust my card vendor to do just one thing, to go look at the error interface and see what's really happening. So you've got that. It allows us to audit a whole bunch of interesting things. Really look at other things that become possible. So you can experiment. You know that in various countries you are, but in the U.S. we have two different bands where you can run unlicensed operation. There are some restrictions on your vision, when you have to be spread spectrum or frequency hopping rate. But anyway, we could build, for example, encrypting transceivers using the same foundation. Yeah. Whether you can encrypt or not encrypt is really it's mostly a problem for the amateur radio operators because their charter is thou shalt not encrypt. But if you look at the web stuff, it actually runs on the 802.11 runs in what's called the unlicensed band.
So it's not the same kind of
You can be free to encrypt away. Oh, absolutely. Yeah.
Unlicensed is not the same as handbands are licensed. That's the whole idea of a hand license.
Yeah, there's a license and there's specific division. Part of the problem I don't know if I call it a problem, but there's so many restrictions in the hand universe that it actually stops progress from being made. So it drives people like me into, oh, I'm licensed band, what tricks can we do over there? I'd like to do these things, I'd like to do this DNA. Yeah, they're not. The thing of it, the question is, the point is that they're not unrestricted. They're just unlicensed. So there are restrictions. I mean, it's basically a good neighbor kind of policy. So there's some restrictions on the power you can run, and there's variations on how much power you can run depending on what direction the antennas are. Not that you're just free to blast, but it turns out that if people cooperate, you can have stuff work. And I know people that are running the 802.11 stuff over close to 15-mile links, offering mountaintops with directional antennas. It may not be technically legal, but it actually works quite effectively because it's not bothering anything. Any other questions? Okay. Well, I have
Ways of
Okay, very interesting, really good question.
Could be cheap.
Absolutely. I mean, and there's the Federal Communications Commission, the FCC in the U.S., issued what they call a notice of proposed rulemaking not that long ago, 6 months ago, which was specifically around software-defined radios. Because how it's been, at least in the U.S., and I think surprisingly, it's a similar type of approval requirement in Europe, is that if you wanted to transmit, you had to meet particularly, you had to say, what band am I going to transmit it? You had to meet all the division requirements of that. I mean, in one sense, there's a good reason for that. You don't want spurious emissions. You don't want to put something that's accidentally smashing vital communications. The U.S. has the funny policy of, relatively recently, of prohibited the reception of certain electromagnetic waves that are passing through the body. Now, this didn't used to be the case, but it was pushed forward by lobbyists associated with the cellular telephony industry in the U.S., particularly when we were all analog. We were $100 scanner was coming down all over the cell phone calls. So there's some things about that. But if you start looking at software-defined radio in general, it pretty much moves that problem. I mean, it's hard. If I build a receiver that that it really just sucks down the whole piece and tunes continuously from 50 megahertz to 900. Okay, good. I promise if you say, pound define USA, I'll put the check in the code that says if def USA, if the frequency is between 825 and 849 megahertz, I'll return error.
But the hardware alone would be out of violation.
The heart is it's not clear. There's some specific things about kits. It's an area that hasn't been tested.
Very good.
Yeah, it's great, absolutely. And describe, what does it say? That the growth as it emerges at the border of chaos and order, right? So we're in that gray zone. Yeah. Yeah, sound card and narrowband, there's a bunch of interesting things you can do. So there's a bunch of narrowband stuff, signals that either pager traffic comes that way. There are a bunch of FSK stuff in the U.S. Some law enforcement stuff uses things that were supposedly encrypted that turned out to not be. The little terminals in the police cars. We're writing things, yeah.
Isn't there somebody using this sort of stuff to do bounce signals off the moon?
Yes, there is. Very good. There's great point. There's a gentleman who seems to be something, and I think it's in the UK or Swiss, I don't remember which one. But he's using basically, it's a narrowband application into a sound, basically a sound higher, it's a sound blaster that's sampled at 96 kilohertz. But he's doing Earth-Moon, Earth communications in a ham band. And he's basically doing all these digital signal processing tricks to manage to pull this signal off of the moon, which is a long way. Once you transmit to the moon, the guy who's trying to receive it's only a quarter of the way around the planet, which makes sense to do that on a very non-shining surface. So that's one. There's
Can you say more about how this software would eventually be usable in embedded systems?
Oh, sure. Is the embedded system, two ways we can go with it. First of all, because all C or C++. So there's we don't make any particular requirement. We're not trying to make it as non-portable as possible. So as the hardware in the embedded system gets faster, we can just run it in the hardware. So there's a question of, because we've got people come and say, well, I want to build a portable radio. That's fine. That's great. If you want to gear up and build a radio, you're welcome to use the software and take it and run it. We're also looking at ways to take this and run it across clusters of machines also. For example, one of the interesting things about this radio, or one of the distinct characteristics, is that pretty much you can predict the data rates out of each block. So you can actually schedule effectively across clusters even when you have non-uniform memory access. Maybe you can schedule this piece here altogether, and then I know I have an socket stream coming out at a particular rate, and I can get across Ethernet. Yeah. Yeah, there's some background information. There's good, there needs to be a site added to it, but there's a really good, if you punch software radio into Google, you'll get a site in France by, I forget the gentleman's name, but it's an excellent set of links on the whole background. Their background papers, if you punch Spectrumware in, you'll get the MIT papers. What drove software-defined radio from the very beginning actually was primarily the military application for doing spectrum management, they call it. And there's some pretty interesting equipment you can purchase today. At least, the U.S. has no control that these guys have money. But they have these really high-speed converters. They have racks of DSPs. They have the racks of FPGAs. They have all the software you can get the big DSP box. They do all kinds of great tricks. Yeah. Field programmable gate array. What it is, it's a piece of hardware that has a whole bunch of pins on it, and you get to put a program in it that says how the pins relate. Okay, I'd also like to say that this project is actually being run through the Crypto Rights Foundation, which is acting as a conduit to get this thing funded. We've been fortunate enough to have people who wanted to provide money to get this done, and we're most grateful for those folks.